Hello guys, this video will cover the Kruskal algorithm. Kruskals is a greedy technique, so we have to choose the edges in our spanning tree based on the greedy technique. In the previous lecture, I have covered the concept of a spanning tree and what is a minimum cost spanning tree. This algorithm, Kruskal's algorithm, is used to find out the minimum cost spanning tree if a graph is given with their weighted edges. So this algorithm is work as according to the greedy approach. So the first step to in order to construct a minimum cost spanning tree is we take the minimum edge first. So always we have to take the minimum weight edge. So in the whole graph, the edge with the minimum weight is this one. So I select this edge with weight 10 initially. So we can apply max-min algorithm in order to find out the minimum edge in this graph, and this algorithm will take order of n time if I apply max-min algorithm. So there are total of e edges. Then we need to delete this first edge and get the other edges, remaining edges. So what we need to do to we can apply the extract min operation of if there is a min heap is there, then we have to apply the extract min. So e edge is already in my min heap. I just extract the first edge by deleting it. So if I have a heap containing e edges, so there is a heap containing e edges which is already in min heap, then I have to delete the min element, that is the first edge, and get that. So this will take order of log e base 2 time. So this is my first step. And second step is, so either I use the min-max algorithm, which will take order of n time, or if I use a min heap approach, then it will take order of e log base 2 time. So either I can make good choice. Always I will make the good choice. So I should choose the heap approach here. Now again, after that, once you selected the minimum edge weight first, then you select the second minimum edge weight. So in my minimum spanning tree, I already taken the edge that is 1 to 2. The second minimum weight is 20. So I just consider the edge from 3 to 4 with the weight 20. Then again in third step, I again pick the third minimum edge. So the third minimum edge in the whole spanning tree is 25. So I just redraw in this graph itself. So this is it, 25. Then I take another edge which is minimum. So the next edge which is minimum is 30. So I cannot include 30. Yes, 30 can be included in the spanning tree. So I just redraw 30 here. 30. Okay, so it should be included. Then the next edge is 40. I cannot include 40 because this will form a cycle here. I can choose 45, and this also leads to a cycle. I can choose the edge with 55. Yeah, 55. This can also form a cycle. 60. I can choose the edge as a 60. So this one. So this edge weight is 60. Now you can see that to reach to the node 6, I have two possibilities. Either I have to go from 4 to 6, or either I go from 2 to 6. Okay, so always we need to cover the or select those edges with the minimum weight. And if I consider this 60, the whole algorithm is means between to reach node 6, I have two possibilities. So if I remove this one, I can pick this one. So in order to select this edge, or in order to go from 4 to 6, you just select the edge weight with 50, and this one is 30. Let's delete the. So the idea is very simple. At each step we need to select the number of edges or the edges with the minimum weight. Okay, so this is one of the possible spanning tree that can be formed. Now let's see what is the complexity analysis of this spanning tree. So we can say that for each of the edge we need to apply operation order of log e base 2. So I apply this operation for selecting 20, then I select 30, then I select 40, then 45. All these edges are go through the time order of log e, and I know that I have n minus 1 edges in my spanning tree. So the time complexity is because this operation is applied on n minus 1 edges, so I can say that the time complexity would be n minus 1 into log e base 2 if the okay. So this may be a case where I can apply this one time complexity. So or I can say that because for n vertices, how many edges are there? For n vertices I have n into n minus 1 by 2 edges. Okay, so in worst case I can say that the time complexity would be, because this is n minus 1, I can say that it would be log e base 2, where e, that number of edges, n into n minus 1 2 by 2. So this time is always greater than this one. So if I consider it as a best case, this is my worst case, e log e. Or in terms of n, I can say that this is order of n square log n square. I put the value of e is equal to n into n minus 1 by 2. That is maximum number of edges that can be possible in my graph. Okay, so the Kruskal algorithm solve the problem in e log e time to find out the minimum cost spanning tree. Now the next problem is Prim's algorithm. This is also follow the greedy approach in order to find out the minimum cost spanning tree. So in this case, if I consider the same graph, so I just redraw the graph so that it is easier for you. There is a vertex from 1 to 2, the edge weight is 10. From 1 to 3, the edge weight is 45. 3 to 4 and 4 to 2, the edge weights are 20 and 30. The diagonal element have edge weight 40, and there is a node 5 with the edge weights 55 and 25, and we have node 6 with the edge weights 50 and 60. So this is the graph given. Now we need to find out the minimum cost spanning tree of this graph. So take the in this case we have to select the vertex we want to traverse. So I can select any vertex. So Prim's algorithm is based on a vertex. So the first step would be select a vertex, any vertex in the graph. and find the adjacents and find their adjacent vertices. So if I pick the vertex number 1, then the adjacent vertices are 2 and 3. These two vertices are adjacent. I just write the cost of these two vertices. One have the cost 10, other have cost 45, and to find out the adjacent vertices, it will take in worst case order of n time, linear time. Now we have to find out the which adjacent vertice is a minimum. So because it is a greedy, find the minimum weight edge with above adjacent vertices. So the vertices that you have find out up till now, I need to select the vertex with minimum edge weight. So I maintain in this algorithm I maintain two sets. So the second step is I pick this edge 1 to 2 because this edge have a minimum weight, and I make a set remaining in which the remaining edges are enlisted or added. So the remaining edge is here is 1, 2, 3 with the weight 45. Okay, now there is another matrix that keep track about the adjacent nodes or adjacent vertices. So in first phase the adjacent matrix have vertices have this one. So I apply so after this the adjacent of 2, because I select the vertex 2, so the adjacent of 2 will be listed here. So the adjacent of 2 would be, I already have 1, I am not including it because it is a bidirectional path. I include 3, 4, 6 with the edge weights 40, 30 and 60. Now we have to select the minimum between the remaining edge of the previous iteration and the adjacent of the current node. Whatever edge is minimum, the vertex is added to my current spanning tree with the condition that there is no looping is formed. Okay, so this finding the minimum edge will take order of n time. So we need to do the steps in 2 arrays, that is remaining one and adjacent one. So at each step order of 2n time would be taken, n plus n time would be taken. So because in these four edges the minimum edge is 2 to 4, I include 2 to 4 in my spanning tree. Okay, so I add 2 to 4 here with the weight 30. When you add any vertex, the remaining and adjacent vertex is updated. Now remaining is 1 to 3 with the cost 45, and 2 to 3 with the cost 40, and 2 to 6 with the cost 60. The adjacent of 4, now adjacent of 4 unlisted because I have selected the node 4. The adjacents of 4 are 3 which is not taken yet, 5 which is not taken yet, 6 which is not taken yet, 2 is already taken, so I am not enlisted it. So in this 3, 5, 6, I just write the code. For 3 it is 20, for 5 it is 25, and for 6 it is 50. Okay, now we have to select the minimum between these all edges set, and the minimum is 20. So I just draw the edge from 4 to 3. So here is 3, just add the edge, and the edge is 20. So similarly again, the next iteration, because so I have taken this edge, now these two edges are added into the remaining set, so the remaining set would be updated as, I have also add the edge from 4 to 5 and from 4 to 6. These two edges are also added, and the adjacent vertex now is the adjacent of node 3. The adjacents of node 3 are 4. 1 is already taken, I am not enlisted it. 2 is already taken, 4 is already taken, I just enlisted 3 to 5 which have the value 55. Okay, so in the adjacent vertex 3 to 5, in these vertices I need to select the minimum one. For 4 to 5 there is a cost 25, for 4 to 6 there is a cost 50. So the minimum cost is from 4 to 5, so I need to select the 4 to 5 here because it is a minimum one. So I just draw 4 to 5 here with the cost 25. Now this is already picked up. Again I update the remaining set as, so the remaining set now contain 1 to 3, I just write it here, 1 to 3, 2 to 3, 2 to 6, 2 to 3 and 2 to 6, 4 to 6 and 3 to 5, 4 to 6 and 3 to 5. Now the edge weight for this one are 45, 40, 60, 40, 60, and 4 to 6 we have 50, and 3 to 5 we have 55. These are the remaining set. Now the adjacents of 5, the adjacent of 5 is, the set of adjacent is the adjacent of 5, because the adjacent of 5 is only, let's see the graph of to find out the adjacents of 5. So it will either take 3, 4. So there are two adjacents. Already I have considered 3, 4 in my graph, so I am not including it in my adjacency matrix or adjacency set. Then the vertex which is taken is from, we take the vertex from the remaining set. So because adjacency set is empty, I just pick the edge with here. So this 2 to 3 is minimum 40. So if I pick 40, then I just see that whether a cycle is formed or not. So I just redo the minimum spanning tree. So I have edge 2 to 1 to 2, 2 to 4, and 4 to 5. This 4 to 5 is 25, 2 to 4 is 30, and 4 to 3 is 20. Okay, now I need to want to add 2 to 3. If I add 2 to 3, so it is not possible. Then again 1 to 3, it is also not possible. Again 4 to 6, yeah, 4 to 6 is possible. So I just add this edge 4 to 6 here with the edge weight 50. So this is not possible, but this is possible. So after that, the remaining set is, I have remaining only one edge, that is 3 to 5, that I can include with the edge width 55, and the adjacency matrix is the adjacent to 6. Now adjacent to 6 are either I can club 2 or 4, and all these two vertices already covered, so there is no updation in the adjacency matrix. So I pick from this remaining, so I pick 3 to 5, so I cannot pick 3 to 5 because it will form a cycle, so it is not selected. Now the remaining set and adjacent set is empty. When this is empty, now it will your final minimum cost spanning tree S. Okay, so this have how many vertices? 6 vertices and 5 edges. Okay, and minus 1 edges. So that for each iteration, as we know that for each iteration I require order of 2n time in worst case. So the total time for this algorithm is order of n square. So if these n steps are taken, then it is, and the total time complexity is nothing but order of n square. So there is a note here, the Prim's algorithm always generate connected graph. So because the Prim's algorithm is based on the adjacency of the current vertex, so it always return the connected graph. But your Kruskal's algorithm does not guarantee to return a connected graph. It may possible that it may generate a disconnected graph, because it will consider the edge width only, not the adjacent vertices. So I hope you you understand the concept of Prim's and Kruskal's algorithm. We will see some questions based on these two algorithms in next video lectures. Thank you very much for watching.